Right, so we are going to begin the session today by discussing a very interesting problem in friction, which is to do with limiting friction, but also we'll have to use the concept of pseudo force a little bit, non-inertial frame and pseudo force concept in order to solve it. So this is going to be I believe, the fifth session of friction for us. Okay. And as I said, as we complete some of these problems, I will keep some time aside for doubts. So any questions that you have difficulty with in the HC Verma or module, etc., please keep them ready and handy. I will ask you to share them and we'll discuss. Okay. So anyhow, let's get on with this question. So we have this kind of a situation. We have a triangular wedge, and this triangular wedge is lying on some kind of frictionless horizontal surface. Theta, the mass of this is capital M. So this surface is frictionless, but this time the inclined surface of the wedge, this is going to have a coefficient of friction. This is going to be rough. Okay. And we are going to place a small block on this surface, and the moment we place this block, we're going to start pushing the wedge with some external force, with the objective that we should be able to keep the block at rest with respect to the wedge. So the block should not slide down the inclined surface even as the system is getting pushed with a horizontal acceleration because of this force F. Okay. So given these values, let us say capital M is 25 kilograms, small m is 5 kilograms. The angle of inclination for this is the standard favorite one, 37 degrees, and acceleration due to gravity is 10 meters per second square. But this time this is rough, so the question is going to be a little bit more interesting to solve. So we have to find the range of values, okay, range of magnitudes for F, which is a horizontal external force. So by range of values, we mean that it can be in between some two limiting values, minimum and maximum. So we have to find the minimum possible to maximum possible value of F, so that this condition is satisfied, that the block does not slide down the wedge. Okay. So just start with the free body diagram. So this is a horizontal external force. So we have to find the range of magnitudes for F such that the block of mass small m does not slip on the wedge, or does not slide on the wedge. So you have to approach it in the same way in which we had approached this problem when we had seen a similar version of it, but the surface was frictionless. Okay. So that time what we had done is we had assumed some acceleration A, and we had seen the condition for equilibrium of the small block M in the non-inertial frame of the wedge being accelerated horizontally at A. So same thing you have to do now here. You'll assume that the wedge and block are moving together with common acceleration A in the ground frame. So then when you get into the non-inertial frame of the wedge, the block should be in equilibrium. But the equilibrium will include one additional force, which is friction. And friction is going to be static in nature because it's at rest with respect to the surface. So that is where the limiting condition concept will come in. Oh, of course, you need the value of mu also over here. So let us take the coefficient of friction to be 0.2. So Anushka, the value given is for capital F or for friction? Capital F. Okay. No, unfortunately, the answer is not correct. Okay, but let me start by explaining the free body diagram concept. So if we assume the system capital M plus small m moves with common acceleration E with respect to the ground frame. Okay. So we are making that assumption now that as we are pushing this with force F, this whole thing is having a common acceleration. So in the inertial frame, we have made this free body diagram in the ground frame. So we will get F is equal to capital M plus small m into E. That's the first thing. Okay. Now for the condition for the block small m's equilibrium, obviously not equilibrium in ground frame, but equilibrium with respect to the wedge capital M. So for that we have to understand the free body diagram in non-inertial frame. So we have to now get into the frame of the wedge. So that is a non-inertial frame. So we are now in the wedges frame, which itself is moving with a horizontal acceleration E, which we have taken like this. So in this frame now what we want that the block should be at the equilibrium condition. So what are the forces that will act on the block? There will be pseudo force. This is your pseudo force opposite to acceleration, mass into acceleration in magnitude. There will be weight. There will be normal reaction. Now comes the interesting part about where friction fits in all of this. Okay. But before that, you know that draw this here. This angle is theta. It's the same as this angle theta. Okay. So if mg sine theta is greater than pseudo force's cos component, then the block tends to slip down the incline. So in that case, if it is at rest, then there should be static friction acting on it. In which sort of direction? In this sort of direction. So this should be the static friction for its relative acceleration A prime to be 0 in the non-inertial frame or with respect to the wedge. Okay. So for this condition that mg sine theta is greater than this, or in other words A is less than g tan theta, the condition for equilibrium is this, that mg sine theta is balanced by the sum of static friction plus pseudo forces cos component. Okay. And normal reaction is mg cos theta minus, sorry, plus ma sin theta. Okay. So we have these two equations. Now friction's limiting condition, that is what, that friction is less than equal to mu n. So from equation 1, mg sin theta minus ma cos theta, this is the required amount of friction. This should be less than equal to mu into n, which from equation 2 is mg cos theta plus ma sin theta. So this is from equation 2 you substitute, and this side you substitute from equation 1. So we get this very interesting inequality that g sin theta minus a cos theta is less than equal to mu into g cos theta plus a sin theta. You can cancel the mass on both the sides. So now we want the condition on a. So take a on one side. So a into, you'll see, you'll get cos theta plus mu sin theta should be greater than equal to, because I've taken this a that side, so the sign is flipped. Okay. So this should be greater than equal to g into sin theta minus mu cos theta. So you're getting a greater than equal to condition on a. That means you'll get the minimum a from this. So this should be greater than equal to this term. Okay. And theta you can substitute as 37 degrees and mu was 0.2. So this will tell us that a is greater than equal to 10 into sin theta, which is 0.6, minus mu cos theta, which is zero point 0.2 into zero point 0.4, divided by cos theta, which is zero point 0.8, plus mu sin theta, so that is zero point 0.2 into zero point 0.6. So a is greater than equal to 10 into zero point 0.6 minus 0.08, so that is 0.52, divided by zero point 0.8 plus 1.2, sorry, 0.12, so that is 0.92. So from this you will get that a is greater than equal to, if you calculate this, it's 10 into 52 by 92. So 130 by 23. Okay. So this is telling me that the minimum acceleration I require, minimum acceleration is 5.65 meters per second. So from that I'll get the minimum amount of force I need to apply is capital M plus small m into A minimum. So that we will get as 30 into this value here. 25 plus 5 here. That will become so about 169.5. newtons. This is the minimum amount of force I need to apply. When I apply this force, I'm having to utilize maximum available friction up the inclined plane to save the block from sliding down the inclined plane. The condition to slide is, I mean, the tendency to slide is to slide down the incline. So friction is acting in this way. Okay. So just go through this once, and then we will discuss how to calculate the upper limit. Okay. So right from here, this is the important thing over here, that we are looking for that condition where mg sine component is dominating. So let me make the free body diagram once more with the forces resolved. If you look at the FBD with the forces resolved, mg sine theta. Okay. Now mg sine theta is trying to make it slide down the inclined plane, whereas your pseudo force, its cos component, is trying to counter that. Okay, but if this one dominates, then friction has to come to the rescue to save it from sliding down the inclined plane. So that is what we are taking in this case. That friction is having to help this. This is our static friction, and of course there is normal reaction in this direction. And not only that, now for the limiting condition, we are taking the static friction equal to mu into n. Okay. So I will basically see that you focus more on this term here. That this is telling us that the minimum acceleration is equal to g into sine theta minus mu cos theta upon cos theta plus mu sine theta. Okay. Just remember this parametrically that we are getting this term. I mean, you don't have to memorize it as a question, but just so from this, the minimum force is capital M plus small m into that minimum acceleration. Yeah, cos theta is 0.8, that's correct. But I think in the next step, I've taken the right value only. So, oh, sorry, I have not taken the right one. Wait, wait. So this is numerically wrong. Okay, you have to make a correction here, people. This will become zero point 0.6 minus 0.16. So the numerator will become 0.44. So this whole value will change. Okay. So then further, F minimum. Okay, so we'll come back to F minimum. Don't worry. Okay, so hope it is all right now. Just check my calculation. So condition for the block small m's equilibrium with respect to the wedge. So the block's acceleration in the wedge's frame, that is what we have taken as a prime, but that should be zero because it's in equilibrium. Is the substitution correct now after the sine theta minus mu cos theta term? Is it all right now? No, if acceleration comes out negative, are you saying that basically means that the direction of motion is wrong? Not necessarily that the value is wrong, but in that case we'll assume that the direction of motion that we have assumed is not the correct direction. It is the opposite direction. Okay, so hope all of you have are clear with this explanation and have done up to the calculation of this A minimum. Up to calculation of A minimum is clear to all of you. So this will tell us F minimum, and the minimum amount of force will become just 30 kg multiplied by that 4.78. So it will come out to be about 143.48 newtons. You can just leave this at first place of decimal actually. Okay, so this is the minimum amount of acceleration or force we need to provide. Now, on the other hand, what happens if in the same situation is the other way around? Suppose on the block, mg sine theta was acting like this, but instead now if my dominating force is the pseudo forces component along the inclined plane, if ma cos theta turns out to be greater than mg sine theta, that is in fact the case, then what will happen is that the block will tend to slide up the inclined plane. Now, if you think about it very carefully, that can happen. The block is experiencing pseudo force like this now. So if the pseudo force becomes very large because the acceleration is too large, it can have a tendency to start sliding up the inclined plane. Okay. So if A is too much, that because of A being too much, ma cos theta dominates over mg sine theta. So this is the reverse condition now. The tendency to slip for the block will be up the inclined plane. Okay. So static friction will act down the inclined plane. So in this case, static friction at this surface will be helping out mg sine theta because mg sine theta is falling short of ma cos theta, and with that the relative acceleration will become zero. Okay. So here the condition will be for equilibrium in this frame. The condition will be mg sine theta plus static friction together is balancing ma cos theta. Okay. And of course, normal reaction is equal to mg cos theta plus ma sin theta. Okay. And the limiting condition is that the static friction cannot exceed mu m. So from equation 1, your static friction required now is becoming ma cos theta minus mg sin theta. Earlier it was the opposite of this. It was mg sin theta minus ma cos theta. Now it is becoming ma cos theta minus mg sin theta. This required friction should not exceed the maximum friction available to us, which is this. Okay. So now just again convert the inequality this way. So this time you take g on that side and keep a on this side. So a into cos theta minus mu sin theta will be less than equal to g into sin theta from this side plus mu cos theta from that side. So this time we will get that a should be less than equal to. That means it gives you an upper limit or the maximum value of this term. This. Okay. So now this is the all important equation for us. So this is telling us that from this the maximum value of a will become this. This time I'll got it right, writing it as 0.8. Okay, so that becomes 10 into 0.76 upon 68, right? So correspondingly, from this you will see that the maximum force this kind of term. So now we can see that our range of values of f has to be between the minimum value we calculated above and the maximum value we calculated here, or 143.4. This kind of a range. Okay, so hope this is clear. Seems like a very massive question right now, but gradually we'll get used to it. Kevin, I'm getting a different value. Is Can we just check? Are you getting the same value of acceleration? Okay, okay. Okay, now I'll just tell you a quick shortcut trick that we can use here. Okay. So see, once you have understood what is happening in this question, now at exam level, how we can do this question faster? Let's try to understand that. Okay, so what we can see is that for lower limit of f, that is minimum value, okay, that corresponds to acceleration's minimum value. Okay, so that corresponds to basically the pseudo force is becoming minimum. So in order to help pseudo force, maximum friction has to act up the incline, because obviously your pseudo force is short. So which force is dominating? The force which is dominating is your this thing, what we call it, the mg sine theta component is the one which is dominating. Okay. So instead of worrying too much about equations and all that, limiting condition and all that, we just straight away we visualize that situation in the non-inertial frame, of course, where this is the minimum acceleration. So it's in the limiting condition, it's just about to slip down the inclined plane. So in that case, we already know that this friction has to be how much? It has to be mu n. So just write it as mu n straight away, okay, without too much worry. And then show the other forces. So mg acting down I mean vertically downwards, and pseudo force acting horizontally like this. So we already know that this is corresponding to the limiting friction condition, because so this is when this is happening. A is minimum. So this angle is theta, this angle is theta. You just write this condition that MA cos theta plus mu n has to balance mg sin theta. That is your first equation. And normal reaction is balancing the sum of mg cos theta plus ma sin theta. So that's fairly easy to understand from this free body diagram. So the corresponding value of A that we get over here, this is equal to the minimum value of acceleration. So correspondingly, the minimum value of force becomes this. So F minimum becomes M plus M into A minimum. So when we do this, when we eliminate N over here and calculate, we can see that our F minimum is becoming G into sin theta minus mu cos theta upon cos theta plus mu sin theta. That is simply coming by solving equation 1 and 2. Okay. And then, so of course, into m plus m, because we are calculating f minimum. Now the second case, now we don't need to do anything else. Now for the maximum case, now pay attention to what I'm saying next. So therefore we'll understand from this only that when I start increasing the acceleration of the system from here by increasing the force, what happens? The amount of friction required is becoming lesser and lesser, till at some stage mg sin theta and ma cos theta balance each other. So that time no friction is required. But if I continue increasing the acceleration, what will happen? Now ma cos theta is dominating over mg sin theta, so friction's direction gets reversed. So from this you understand that on the other hand, that for A being the maximum value, what is happening is maximum static friction of mu n will act down the inclined plane. So you just visualize the free body diagram. The rest you don't have to do anything. For the equations, I'll give you something very convenient now. Okay. So if you compare this free body diagram to the above diagram, you can see only one change has happened. The direction of mu n has got reversed. Baki sare forces, pay attention, you will see they're exactly the same in this free body diagram and the above one. So everything else is the same. The only thing that has changed is the direction of mu n. Okay. So for this one, whatever result I'll get will be, I can get by just reversing the direction of mu n in this equation. So from this equation, I can see that what will happen is that F maximum will be wherever there is mu, replace it with minus mu. So it will become G into sine theta plus mu cos theta upon cos theta minus mu sine theta. This is your maximum acceleration. So that into m plus n is your next. So we can do this directly. We don't need to understand anything else. So see what is happening in A max case. The direction of mu n is reversed compared to A minimum case. Okay. So to come to this, just replace mu n with minus. I mean, just replace mu with minus mu. I mean, originally to start with, you'll do that. Replace mu n with minus mu n. So when you do that, whatever final solution you get, final equation or final formula, wherever mu term was coming, you have to replace with a minus sign. So for the final formula, replace mu with minus mu. That will just take care of this condition. So that is a little shortcut trick that I'm telling you, you can use. If you have already got the limiting condition on friction for friction acting up the inclined plane, then you can get the limiting condition for friction acting down the inclined plane from the same formula that you developed, but just replace with mu with minus mu, because the direction of friction is getting reversed, magnitude is remaining the same, it is mu n. So this can save you a lot of time. That's what I'm saying, Sneaky, that you will get this F max ka equation from the F minimum equation only. Because you compare these two FBDs, you have just reversed your direction of friction. So whatever we had written mu n in equation 1 and 2 here, the corresponding equations that you will write over here in this, which I have not written, but the corresponding equation 1 and 2, you will put friction on the other side. No? So that is the same thing as replacing mu n with minus mu n. So then when you solve this new equation 1 and 2, whatever result you get, it will be exactly same as this, but the mu is replaced with minus mu, because wherever there was mu in my equation, it had to be reversed in direction. So it had to be replaced with minus mu. So in the minimum wala equation, just replace mu with minus mu. So you'll see you'll get the maximum one equation. So that is the shortcut I was telling about. That is the shortcut trick you can use, that you found limiting condition in one direction. So you can now just easily generate the limiting condition in the other direction. Yeah, it can be na move, because it, see, pseudo force का cos component कितना है compared to mg sin theta, that depends on E na, the acceleration we are giving to the system, and the acceleration we are giving to the system depends on the force we are applying, no? So in the above thing we saw that when we applied the force of that, whatever the maximum limit was, 200 and something, we had to actually apply maximum friction down the inclined plane, no? So obviously pseudo force was dominating in this 335 wala case, whereas in the 143.4 case it was mg sin theta which is dominating. So that is that relationship between the pseudo force's cos component and mg sin component, that is completely controlled by the force that we are applying, the external force F. So it can have any value, no? Now if I apply a force of more than 335 point whatever, 335.4, then friction won't be able to prevent it from sliding. So you'll see that very strange situation, that as you're pushing the wedge towards the left, the block will be sliding up the inclined plane. Now if you think about it very carefully and try to visualize, you can understand that that will be happening. If you're pushing that too fast towards the left, you will realize that the block will tend to slide up the inclined plane. It's a very unlikely situation, but it can happen. Why unlikely? Because you have to apply a lot of force for that. The acceleration has to be really very large. So hope this is clear now. Okay, so now I'll give you a question which is based on an IIT question, but long time ago in IIT, when IIT used to be a subjective paper instead of being, all MCQ type of questions. So this is from sometime in the late 1990s in IIT-JEE entrance. It was called that instead of JEE Advanced. It was called IIT-JEE entrance exam at that point of time. Okay. So this is a smooth surface. This is a wedge of mass capital M. Now on this wedge, there's one smaller block here and one smaller block here. So having a pulley attached to the wedge, a massless pulley, and these two blocks are connected by massless threads like this. So these two are of same mass. And now the important thing is that this surface is having coefficient of friction mu, which is the same that this surface is having. Okay. Now in order to keep these from sliding down, I mean from the one on the side from sliding down and the one on top from sliding towards the right, we're actually pushing the system with a horizontal force F. Okay. So again, find the range of values of magnitude of F such that the two identical blocks, small m, do not slip with respect to the wedge of mass capital M. Okay. So here you will get the range of F in terms of the given quantities, that is small m, capital M, and mu, and of course G, acceleration due to gravity. So try to work this question out. So same procedure. Okay, only now there is the added complication of a thread and a pulley. So once again, pulley is massless and smooth. The thread is also light or massless and inextensible. Okay, so just work this out, people. Sorry, I'm just Yeah, so we have to get all the answers in terms of the quantities given in the question. That is capital M, small m, and mu, and of course G. Okay. So here also, if we now visualize the situation where you are applying the minimum force, okay, minimum force case. So the horizontal acceleration is minimum. So the pseudo force is minimum. So what is happening? Limiting friction will act in both blocks, okay, to prevent slipping down for one block and to the right for the other one. So once I make the free body diagram, this will become clear to you why this is the case. So now instead of putting so much time into making separate FBDs and all that, you can just do everything in one common diagram. So you don't want to change the shape of the pulley, that would not be correct. So now because I'm going to use this diagram once more, so I'll just make a copy of it. But yeah, for the minimum case, let's work out first. So if this system is moving with the minimum common acceleration in the ground plane, then to this person in the non-inertial frame of the wedge, they should be at rest. They should be at rest. Okay. But limiting friction should act in this manner, which I am showing above. That limiting friction should act on this block in such a way to it is preventing it from slipping down the inclined plane. I mean down the vertical. So here limiting friction should act, and this one from moving towards the left. So this should act. Okay. So let's say this F1 and this is F2. Now these will be limiting values. So I'm coming to what these limiting values are. Now let's list the other forces. So there is pseudo force on this. Remember the blocks are of same mass, small m. This E is of course the E minimum. Yes. There is mg, mg. There is some tension in the thread. And finally, there are some normal reactions that are acting between the this one. So let's say this is N1 and this normal reaction here is N2. So that tells me that this being limiting friction, F2 should be equal to mu N2. And this also being limiting friction here, F1 should be equal to mu N1 when this is happening. Okay. So hope this is clear to all of you. Yes, Kevin, I think your answers are correct. Seem to be correct. Yes, yes, they are correct in fact. So now let me solve the two FBDs for the minimum acceleration condition. Okay. So for this, so for the one block we have MA plus mu N1 is balancing T and N1 is equal to mg. Okay. So from these two we will get the condition that MA plus mu mg is equal to T. So this is our first equation, let's say A for the block A. Now similarly for the block B, we will have the condition that T plus mu N2 is balancing Mg, and N2, the normal reaction, is equal to the pseudo force on this. So solving these two, we'll get one independent equation that T plus mu Ma is equal to Mg. So this is equation B. Okay. Now we will solve equation A and B together to get the value of acceleration, and that will give us the minimum acceleration condition. Okay. We'll need this later. Okay. So now solve these two to eliminate tension. So you can just add them. So you can see that you'll get, if you just add the two equations, T on either sides cancels out. So you get Ma plus mu Ma plus mu Mg is equal to Mg. So you get A as G into 1 minus mu upon 1 plus mu. So this is basically which acceleration? This is the minimum acceleration. This is A minimum. G into 1 minus mu upon 1 plus mu. So this will correspond to, now if you take the whole thing's FBD, now, combined free body diagram kind of thing. So this whole thing is moving with this acceleration A, and there's no friction on the ground. So F minimum is equal to total mass of the system into A minimum. So from this you are getting the minimum force we have to apply as this quantity M plus 2M into G into 1 minus mu upon 1 plus mu. Whatever the value of mu, obviously we are taking that kind of case when mu is less than 1. Okay. Now you come to the maximum case and you realize that all you have to do is flip mu. So for the situation where we are taking sorry people, I just got disconnected. Yeah, so I hope you haven't missed out too much. I got disconnected, I think. So anyway, I will just share the screen again. Yeah, it's audible now, Snikita? Yeah. Yeah, so coming back, when we have this maximum pseudo force condition, the tendency to slip is the other way. This block has a tendency to slip towards the left, and this block has a tendency to slip upwards because the pseudo force is too much. So tendency to slip for A is left and for B up. So we want that A maximum friction such that for A it is towards the left, towards the right, and for B is down because it tends to slip up. So back to this diagram, this non-inertial frame, which is moving with A equal to maximum acceleration. Yeah, sorry people. Once again, I got disconnected. Some issue with my internet connection happening. So anyway, I'll share that file again. Let's. Yes. So coming back to this maximum case now. Okay. So you understand this is what is going to happen. This has a tendency to slip towards the left. So friction act will act on this like this, and that too limiting friction. And this has a tendency to slip up because the pseudo force acting on this guy is too much. So इस पे friction ऐसा act करेगा. Okay. So the whole thing will be something like this now. But as you know, we don't really need to solve the whole thing now because okay, we can guess the solution by understanding that compared to the above diagram, only friction's direction has reversed. So we can just copy the equations and replace mu with minus mu, and that will do the job. So that there is that shortcut method again I was telling you about. So this is your FBD, and for A equal to A max, both these frictions are limiting friction. Mu n1, common value of mu. So okay, this question becomes even little bit more lengthier if we have different values of mu. I mean the expression looks more lengthy. That's all, but same method of solving. Okay, so I now know from this that A max will just become G into 1 plus mu upon 1 minus mu. How I know this? I know this by replace mu in a minimum case with minus mu, and you'll get this. So therefore the maximum force will become capital M plus 2 times small m, G into this factor 1 plus mu upon 1 minus mu. So you can write the equations for this FBD and verify this later also when you are revising this. But you will see that this trick is very very handy in this type of question. It saves you 50% of time literally. Yes, sure. Yes, Vaishnavi, whenever there is this type of question where we are looking at a range of situations, minimum to maximum, where that range involves the direction of friction changing from, or more importantly, that as we explore that range, the tendency of slipping will change from one direction to the opposite direction. So if the tendency of slipping is going to flip in direction, the direction of static friction is also going to flip. So in the limiting condition, if there is mu(n) acting in one direction, then in the second case, in the other extreme of the range, what will happen? The same mu(n) will act in the opposite direction. So in this case, for example, there are two mu(n)s acting, mu(n1) and mu(n2), but both of them are flipping, going from one extreme to the other. So this trick can be used. So as you solve, more and more questions, you will start getting the experience, like where to use what shortcut. But definitely, if you remember this shortcut in these two questions, then when you are doing a question of this type, you'll know what to do. You'll have that idea beforehand. Okay, so hope you are clear with this. Okay. Now next I will do a question which is similar to a question in HCV. So some of you might have seen this question or may even have a doubt with this question, but I want to discuss this question anyhow. So it is somewhat related to what we were doing last time also, when we were seeing those blocks against the wall, that kind of situation. But here, both the language of the question and the question itself is different in a slight way. It's a bit tricky. So again, this is a rough wall. Okay, and it has a coefficient of friction of, let us say, 0.2. And now what we are doing is we are keeping a single block this time of mass 10 kg, pinned against the wall by applying a force F like this. Okay. So obviously the first thing is that you want to find the minimum value of force so that the block remains in equilibrium. Okay. And take G as 10 meters per second square. So this you know how to do. Now in the second case, what is happening is that we are applying the force of, let's say, uh, 800 newtons. Okay. And another horizontal external force is applied on the block. So this is where you have to understand the language of the question very carefully. Okay. So another horizontal force F prime of magnitude F prime equal to uh, 75 newtons is applied on the block tangential to the wall. Okay. So find the acceleration of the block, if any, okay, and friction acting on it. Okay. So obviously the first part is too easy. The main thing is for you the second part. Understood? Now this is a vertical wall. acceleration due to gravity is acting like this. So we'll just make a correction. We'll make this force 600 newtons. Okay. This force in the second part is not 800 newtons. It is 600 newtons. You can solve it for 800 also, but it will not test the concept that I'm looking to test. So think very carefully about this force F prime. Okay. Follow the language of the question very carefully and visualize. My hint is that you have to visualize this in 3 dimensions. I have given you in the diagram only the side view, but you have to visualize this problem in 3 dimensions to exactly understand how F prime is acting. Yeah, additional force of 75 newtons. Okay. So you are applying F equal to 600 newtons Aman, like it is made in the diagram. F is exactly in the same way it is made in the diagram. Horizontal force acting normal to the wall. But in addition to that, another force F prime is acting. Okay. Yeah, Kevin, the first part is correct, obviously. Yes, Nikita, first part is correct. Good. Yes, Manas, correct. No, Asmi, you have to think some calculation mistake you made. Okay. Now, ideally, you should also write down over here that F is a horizontal external force, though the diagram is showing that to you. Okay. Normal to the wall, perpendicular to the wall. So that information is there in the diagram already. Okay, Asmi. So yes, correct. Second part, I have to just check your answer 1 minute. Uh, no, just check for some minor calculation mistake in second part. Acceleration is not correct, Manas and Suyash. Acha, first of all, tell me what do you think should be the direction of acceleration in the second part? How will the block be sliding? In which direction it will be sliding? Uh, Jenny, you almost got the question correct, but then you're forgetting about gravity also, na? See, there is one force which is in the direction which you have shown me. That is correct. Okay, it can be either of the two directions, like you're saying. But उसके साथ gravity भी तो है ना? So I'll just give you a hint to understand what I'm saying. That see, when we have a block against a surface which is trying to slip on the surface, then what is the force we have to consider which friction is trying to counter? मतलब friction किसको oppose करने की कोशिश कर रहा है? The net tangential force, the net force which is tangential to the surface. Now in this case the surface is the wall, no? It's a vertical surface, so that net tangential force includes gravity. That is where the question is really interesting. Ha, correct, Anushka, that's correct. Manas, very good, the answer is correct. Okay, in fact, Anushka, you can calculate the exact angle also. Kevin, very good, that's correct. Okay, so I'm just making a diagram that will make things clear. Obviously, first part, most of you have got. You'll see that this F will come out to be, F minimum will come out to be mg by mu when you calculate it parametrically. So it will come out to be 500 newtons. Okay, because in this case, your free body diagram is like this: F normal reaction, static friction, and mg, and you want equilibrium. Okay, so you can just figure it out from that. Second case, I'll just make a diagram to explain what is happening, and then I think most of you can figure it out yourself. So if I make a sort of three-dimensional diagram, you'll understand that if I'm viewing this block like this, it's against the wall, it's against this wall like this. So gravity here is acting in this direction. Okay. Now see, this is the unit vector normal to the wall. Okay, and this is a direction which is tangential to the wall but horizontal, and this is the one which is vertical. So these are three axes which are mutually perpendicular. Okay, this is normal, this is, this one is tangential but horizontal. Okay, So this is tangential to the wall, that is okay, but horizontal. Okay, and this is also a horizontal axis, but normal to the wall, and this is your vertical axis. So now you'll understand the force F that I'm applying is along the normal into the wall like this. But the force F prime that I'm applying, that is either like this or like this. So let me assume that I'm pushing it like this. F prime is like this. Okay. And gravity in all of this is like this. Okay. So now I can't really show all the forces in this. I'll struggle a little, but let me try anyway. So normal reaction that the wall is applying, that will be coming out of the plane. It's acting on that other surface. Now the thing about friction. Now friction story becomes very interesting. So this is where I will divide it into a system of axis. So I'll take this as my xy plane, and I'll take this normal direction as my z axis. Okay. So first let me visualize the diagram in the xy plane now. So the xy plane, if I look at it, ब्लॉक पे क्या क्या फोर्सेस मुझे दिखेंगे from this side. I'll see mg acting vertically downwards. I will see f prime acting like this. Okay, and I'll have to figure out the direction of friction. But you can see that the vector sum of these two will become your net tangential force. So friction will have to oppose that. So I don't know whether it is static friction or kinetic friction right now, but some kind of friction is opposing it. So it will have to be opposite to the vector sum of these two. Okay. Because this is the xy plane is the tangential plane to the wall. So in this, the friction opposes the net tangential external force. So the net tangential external force here is the vector sum of this mg and this f prime. So that's why in the diagram I've shown like this. And now if I also visualize in the yz plane, then I'm seeing the diagram the way I had seen earlier. So this is the wall basically. So in this I will see the other force, the force that I'm applying normally like this, and the normal reaction. Okay, and I'll also be able to see mg, but the other forces are tangential. So let's say I'm not drawing the vectors. So this is a truly three-dimensional problem. Okay, so hope these two free body diagrams are clear. Now, to show all the forces, I've of course shown them minus the friction in this one, in this three-dimensional case, but it's really difficult to show. Friction will be in some kind of direction like this, tangential along the wall, so it will get confusing. So I've drawn two separate FBDs. Okay, this is in the vertical plane, the one below this one. This is in the vertical plane. So using mg and these two horizontal forces. Okay, so here what is happening? The net tangential force will have a magnitude of square root of mg square plus f prime square. So that when you work out, you see it's 100 square plus 75 square. So is that nice 3, 4, 5 kind of triangle thing? So it's 125 newtons is the net tangential force acting with respect to the wall. This is the net external force tangential to the wall, but barring friction. Okay, excluding friction. Okay, so this is the force that friction has to oppose. Okay, so this will give the block a tendency to slip, but slip in which direction? The direction like this. This is the tendency of slipping in the xy plane. Okay, so even that angle you can work out, because see, this is your, this angle, suppose it is theta. So this angle will become tan inverse of mg by f. So it will become 53 degrees. Because mg is 100 and f prime is. So मान लो अगर फ्रिक्शन नहीं होता, then the net force on it only would be 125 newtons. So it would accelerate in this direction with a magnitude of 125 divided by the mass. So 12.5 meters per second square. But now we have to check friction also. Now to check friction, we have to see how much friction is available to us. Then we can see whether friction can do the job of preventing slipping, that is static friction will be acting, or friction is not able to prevent slipping, it opposes slipping and kinetic friction acts. So for that we need this. So from this we can see that the normal reaction provided is just nothing but the external force, which is, in this case it was how much, 600 newtons. So from this we can see that the maximum static friction available or limiting friction available is mu n, okay, which is becoming 120 newtons because mu is 0.2. So now we compare these two guys and we see that okay, this is only 120 and this one is 125. So the tangential force is dominating. हाँ नहीं क्यों नहीं consider yes Nikita देखो because that is the two forces we are considering F prime and mg, they are in which frame, they are in which plane, they are in the tangential plane na, they are along the surface, so they are the ones that are trying to create slipping, whereas F जो है जो 600 न्यूटन फोर्स है that is perpendicular to the surface ना, so it's not trying to make the block slip, it is trying to grip the block against the surface by creating normal reaction. Understand na? So the block is against the surface, so there are two types of contact forces. Normal contact force, so who is creating normal contact force? The external force F, which is putting the block against, pressing the block against the surface. But then who is making the block trying to slip? So those are the tangential forces. There are two in number here, mg and f prime. So together their net is that 125 at that angle of 53 to the horizontal. So that was the tricky thing to understand. That if you look at mg individually, it is not enough to make it slip here because we have 120 newton friction available and mg is only 100 newtons. If you look at f prime individually, it cannot make it slip along the x-axis because it's only 75 newtons. But now mg and f prime are both acting together. So they are having a tendency to make it slip with a force of 125 newtons at that diagonal kind of direction. But we have up to 120 newton friction. So there will be acceleration, but relatively lot less acceleration. So we are now seeing that the net tangential force was 125, which is basically square root of mg square plus f prime square. And the maximum friction is only 120 newtons. So therefore the block will slip. But where it will slip? It will slip in the xy plane. That is the plane of the wall. It will neither slip vertically nor slip horizontally. So for that, let us come back to the free body diagram in the xy plane, in the plane of the wall. This is the wall surface. So in that, f prime was like this, 75, mg was like this, 100. So their vector sum would have been in this direction, 125. So now friction will act opposite to that. Okay. And had this friction being equal to 125, then acceleration would have been 0. But this is only 120. So actually the net force now on it is the vector sum of these three. It is mg's vector sum with f prime, vector sum with this kinetic friction. But that vector sum works out to be square root of mg whole square plus f prime square minus mu n. Or it works out to be 125 in this direction minus 120 in this direction. So hence the block has an acceleration which is very interestingly in this sort of diagonal direction. This is the acceleration. So 125 minus the magnitude of the net force, that should be equal to mass into acceleration. 125 minus 120 is equal to 10e. So our acceleration will be 0.5 meters per second square in magnitude, but as you can see, it will be in the xy plane like this. So according to the unit vector notation and all, if you see that theta is tan inverse of mg by f prime, so it will come out to be 53 degrees. So this a, if we want to write it as a proper vector here in my coordinate frame, of course I have chosen the coordinate frame this way. So this is x, this is y. So the x component will become how much? It will become cos 53 I cap, and the y component will come with minus sign because y axis is upwards. So minus sine 53 j cap. So when you work that out, you will see you will get this as um, 0.3 I cap minus zero point 0.4 j cap in meters per second square. Or you can say like this, that the acceleration has a horizontal component of zero point 0.3 and a vertically downward component of zero point 0.4, and the net acceleration is therefore zero point 0.5, but in some sort of diagonal direction, I guess. So that's the interesting part about this question. Okay. So I mean, these are really the more tricky type of questions. So don't worry about the fact that it's taking time for you to analyze and understand the question. The thing is, you're learning a lot of things from the question. You're learning to connect all the concepts, the three-dimensional geometry, limiting friction, component algebra, vectors. So it's it's really, your physics is improving in many ways by exploring questions like this. Okay, so the two free body diagrams drawn in the two different type of planes are clear, because that is really the key to solving the question. Understanding the forces that are visible in the tangential plane to the wall and in the vertical plane containing the wall. Okay, now one final question for today. We'll do simple question. This one is more about just calculating things accurately. So you should be able to work it out. So we are having this inclined plane. Now, in case you're wondering why I always use 37 degrees instead of 30 and all, it's just convenience because I don't want square root of 3 and those kind of numbers to be there in the calculation for that reason. So block A and B are connected by a thread. So blocks A and B are of identical mass, m equal to 5 kg, okay, and connected by a massless inextensible thread. Okay. Now A and B are released from rest simultaneously. So you're like holding the two blocks and releasing them simultaneously at t equal to 0 with the thread taut. So you know you're holding them at rest but with the string kind of stretched out. So with the thread taut, find their accelerations and tension in the thread if coefficient of friction for A is equal to 0.5 and coefficient of friction for B is 0.8. Oh, sorry, 0.8 will become, actually it's okay, but still 0.6 less. Okay, and this part reverse. Coefficient of friction for B is zero point 0.5 and coefficient of friction for A is zero point 0.6. Okay, so just quickly work out in your mind that what are the possible things that can happen and which of those cases those things will happen. Can it be that they will move together with common acceleration? Can it be that A will move faster than B? Can it be that B will move faster than A? What all cases are possible? And what is the condition for those cases to occur? Then you will have no difficulty in working this out. You just try it. It should not take more than 3-4 minutes. This question. Yeah. So see, Kevin, to understand here, ki, you know that if you release a block independently, okay, its acceleration on a rough surface is how much? Its acceleration is g into sine theta minus mu cos theta. Okay. Yeah. Good. So you'll see that in the first case, what is happening, because coefficient of friction of A is less than coefficient of friction of B. So that means A, the block A will tend to accelerate faster, but then the string will come into play. It will pull against the spring. So A tends to accelerate faster. Okay. Hence pulls on the string. Okay. And acceleration of A becomes equal to acceleration of B. Okay, which we'll find out how much it is. But in the second case, mu A is greater than mu B. So that means A accelerates slower than B. So basically, the string loses its tautness. It just becomes loose. And acceleration of A is less than acceleration of B. So basically, B approaches A. Starts to approach A and eventually might collide also. So in this case, acceleration of A will not be equal to acceleration of B. But tension will be zero because the string has become taut. Whereas in this case, they'll have common acceleration, but the tension will not be zero. Okay. So now based on that, you just make the Fbds. Okay. So for example, in the first case, you'll take common acceleration for both of them and assume there is some. So these are the forces along the inclined line. So in the first case, acceleration of A is equal to acceleration of B equal to A, suppose. So for the block A, we have the equation mg sine theta minus mu A into mg cos theta minus T is equal to ma. And for the block B, we have the equation mg sine theta plus T minus mu B into mg cos theta is equal to ma. So add the two equations. It's very simple. Mg, if you take common, 2 sine theta minus mu A plus mu B cos theta is equal to 2ma. So A will become like this. It will become G into 2 sine theta minus mu A plus mu B cos theta divided by 2. So it will become 10 into 2 into 0.6 minus zero point 0.5 plus zero point 0.6, 0.8 upon 2. Okay. This is okay. This is what is happening in the first case. So people, first thing you have to understand this case, when they'll have common acceleration and therefore there will be tension in the string, when they'll have different acceleration because A is moving slower than B. So that is coming from this condition, okay. And then when you solve finally, so this is giving you A equal to 1.6, and when you put in this equation you will get the tension also, okay. So I'm not solving for tension, you can complete that later. And the second case ulta ho jayega na, their accelerations will become different. So second case is very easy actually. Second case, tension is 0, acceleration of A will simply become g sine theta minus mu A cos theta, okay. And acceleration of B will simply become g sine theta minus mu B cos theta. So it's that regular formula. So acceleration of A will come out to be 1.2, is it? And B will come out to be 2. Okay. Okay, people. So hope this is clear to all of you. So there is a similar question in HCV where instead of a string between the two blocks, the blocks are actually kept against each other. तो उसमें उल्टा हो जाता है. उसमें क्या होता है that when tendency for B is to move faster, they will actually move together because B will be pushing A with a normal reaction force. Whereas when tendency of A is to move faster, they lose contact and there's no normal reaction. Here there's a string attached between them, so it's the reverse case. They will have common acceleration when A has a smaller coefficient of friction and tension is non-zero. Okay, people, so hope both the parts of this question are clear to all of you. And just the value of the tension here looks like it is 2 newtons. Just verify that later also. We have to just substitute the value of A back in one of the two equations. But shouldn't it be like 20 newtons instead of 2 newtons? Because the mass is how much? 5 kg, no? Okay, anyway, I'll check and let you know. Yeah, 2 newtons is correct. All right, people. So with that, we come to an end for today's class. So hope you have understood friction till date. Okay. So first and foremost, most importantly, wish you all a very happy Diwali, and make sure that you enjoy the vacation, Diwali vacation, with your family and friends, and get a decent break so that you can recharge yourself for the next part of your learning. And thank you for your wishes, and wish you all very prosperous next year after Diwali also. Very important year for you academically. Okay. And of course, if you do manage to find 1 or 2 days out of your Diwali vacation, then please do a review of your entire physics till now, and whichever areas you have found tricky, whether that is pseudo force or it is limiting friction or some part of vectors, maybe coplanar vectors or things like that, just try to revise that part, and if there's any difficulty, note it down so that when we are back after Diwali vacation, you can discuss that with me. Okay. So once again, happy Diwali and wish you all the best, people. Enjoy your vacation. Sure, I will send an additional assignment also. So once you have completed the module, you can do that assignment. Okay. That assignment will have the type of questions that you can see in DC Pandey also.